Thank you for doing. Thanks for the introduction, and thanks to the organizers for the invitation and for making this event happen under these circumstances. So, close this. So the main idea behind this title is that stochastic and multiscale analysis are intimately connected, not only from a modeling perspective where you randomize your underlying medium to move beyond assumptions of periodicity, but also from an inference perspective where you randomize the solution of a possibly deterministic PDE to represent the loss of information occurring in homogenization, and then you condition on partial information to recover good correctors. And I'm very precise what I mean here. Now, these connections are not new. They can be traced back to interplays between statistical inference and numerical approximation, which are also intimately connected through the process of making estimation with partial information. And the main point that I will try to convey in this talk is that these connections are not just objects of curiosity. You can use them as a pathways to simple solutions to fundamental problems in both areas. And I'm going to illustrate this point based on joint work with Clint Scovel and Florian Schäfer from Caltech, Tim Sullivan from the Free University of Berlin, and Matthias Katzfuss from Texas A&M. So our setting will be that of a linear, symmetric, positive, invertible local operator mapping some subpolar space HS0 of omega into its dual space. So here S is an arbitrary integer that is greater or equal than 1. Omega is a regular bounded domain of RD. And by this L being local, we simply mean that the energy scalar product between U and V is 0 if U and V have disjoint supports. As an example, if S is equal to 1, we can take L to be the following divergence form elliptic operator. These coefficients A can be periodic, stochastic, or completely deterministic and rough with no structure at all. If S is equal to 2, you can take this L to be this higher order PDE, but this L is arbitrary, is a priori completely arbitrary. So one point that I would try to make is that there is something universal about the homogenization of elliptic operators. Now, we're going to write G for the Green's function of that operator L, so that the solution of the system LU equals F can be obtained by integrating F against that Green's function. Okay? Now, because this Green's function is a symmetric positive definite kernel, you can consider the Gaussian process with mean 0 and with covariance function that Green's function. Now, if S is greater than the dimension of the space over 2, then this Green's function is continuous, and this Gaussian process is a centered Gaussian process in a classical sense, meaning that it is mapping each point X of the domain omega into a centered Gaussian random variable, and the covariance between Xi at X and Xi at Y is given by G of XY. If S is arbitrary, then you have to define this Gaussian process in a weak sense as a Gaussian field. So to do so, you integrate it against an element of the dual space, and you define this integral to be scalar valued mean 0 Gaussian random variable with variance, the double integral of phi against the Green's function. Okay. Now, what is the connection between this Gaussian process Xi and the underlying operator L? To answer that question, let's look at an optimal recovery problem. So assume that you have an unknown element u of hs0 of omega, and given its values at m points x1, x2, xm in the domain, you want the best possible approximation of u. So here we assume that S is greater than the dimension space of the space over 2, so that U is continuous and these pointwise values are well defined. And by best, we mean minimax optimal using the relative error in the energy norm of the operator as a loss. Well, it turns out that the U minimax approximation of U given those measurements is given by conditioning this underlying Gaussian process Xi on the observation of the values of U at those endpoints. Okay. Now, why is this Gaussian process Xi giving us the optimal approximation of U? To answer that question, we have to take that minimax problem and lift it to an adversarial game opposing two players. So let's call them 1 and 2. In this game, U is going to choose, player 1 is going to choose an element U of the solution space HS0 of omega. And player 2 gets to see M linear measurements made about U. So here we're going to represent those linear measurements by taking the dual product of U with M elements of the dual space. We're going to write them phi1, phi2, phi-m, and we will call them measurement functions. So the task of player 2 is to recover what U is based on those measurements. So his recovery is a function of those measurements. He makes his, player 1 makes his choice, player 2 makes his choice, and the two choices get combined, and player 2 receives a loss, which here is a relative error in the energy norm of the operator. And the question is, if you are player 2, and if you have to play this game many, many times, how would you play it? Now, before I answer that question, let me just say a few things about why we should care about this game. The reason why we should care is because this is implicitly the game that you are playing when you're trying to upscale, homogenize, or compute fast with partial information. So this is why you want to play it efficiently. Now, on the other question, which is how should you play this game? Well, we know from the seminal work of Wald and von Neumann that zero-sum games have mixed strategies as optimal strategies. So this game is no different, and we can show that the optimal strategy of player 1 is to randomize U according to the distribution of that Gaussian process Xi that we have just defined. And the optimal strategy of player 2 is to assume that player 1 is doing that and recover U by conditioning that Gaussian process Xi on the M linear measurements made on U. Now, this optimal bet of player 2 is not only optimal in the sense of the game lifted to measures, it is also optimal in the deterministic minimax sense of optimal recovery of Michelin-Rivlin. But it is not random. It is a deterministic function of those M linear measurements. And the reason why it is a pure strategy has to do with the fact that we are using a norm, which is a convex object, to define a loss here. And the reason why Xi is an optimal strategy for player 1 has to do with the fact that the norm that we are using here is a quadratic norm. If you were to use L1 or something else, you will find a different distribution. Okay. Now, because this optimal bet of player 2 is obtained by conditioning a Gaussian process on linear measurements made about that Gaussian process, we have a representer theorem, and this optimal bet of player 2 can be written as a linear combination of those measurements. And the coefficients entering in these linear combinations have a dual interpretation as optimal recovery splines in the sense of Michelin-Rivlin, or as elementary gambles or bets, so we are going to call them gamblets for playing the game. So as optimal recovery splines, they're obtained by taking this measurement functions phi and pulling them back by the inverse of the operator L, and taking their linear combinations with the inverse of that matrix theta, which is a Gramian. And as optimal bets, this psi I is simply the best bet of player 2 if he is told that the dual product of phi j with u is delta ij for all j, where this thing is the Kronecker symbol. Okay. Now, what I want to show you is through several examples coming from multiscale and numerical analysis is that if you take this point of view, the point of view of these interplays, you can make some problems that you find in multiscale or numerical analysis very simple. And conversely, you can also make some problems that you find in statistical inference very simple. So the first problem that we are going to look at is a problem in numerical homogenization, where given an integer m, you want to find m basis functions such that these basis functions are as accurate as possible in approximating the solution space of that operator L with the right-hand side that is in L2. And at the same time, you want these basis functions to be as localized as possible. Now, this is not a trivial problem because these two requirements are conflicting. And you can see that by observing that the optimal basis functions for accuracy are the first m eigenfunctions of that operator L, and these eigenfunctions are completely delocalized. Okay, so this is why we in the numerical homogenization community, we have spent a lot of time trying to guess what these numerical basis functions could be. And in fact, these basis functions are essentially the equivalent of correctors in periodic homogenization when you move away from assumptions of periodicity. And what I want to show you is that if you take this, again, this perspective of this Gaussian process regression, this problem becomes very simple. So what do? So assume that this is your domain omega. It doesn't need to be unit square, but let's use that as an example. You partition it into subsets of resolution h. Then you take your measurement functions to be indicator functions of these subsets. Or if you have enough regularity, so if S is greater than d over 2, you can take them to be masses of Diracs centered at these subsets. Then you take your Gaussian process Xi, you condition it on elementary measurements defined by these measurement functions, and you obtain your optimal recoveries splines psi i's. And these basis functions are going to solve our numerical homogenization problem in the sense that they're going to achieve the Kolmogorov and width accuracy up to a constant, meaning that up to a constant, they're going to achieve the same accuracy as the first m eigenfunctions of the operator L, and they are exponentially localized. They decay exponentially away from the support of these measurement functions phi i's. Okay, so this is what these basis functions look like. This is a slice, and this is a log scale plot of this plot. So you really see this exponential decay. Okay, now this exponential decay result is a generalization of result by Malmquist and Petersheim and Kornhuber and Petersheim and Yefentant on the local orthogonal decomposition method. Now, one interesting thing is that this localization result that you get from the numerical analysis perspective is actually going to solve an open problem in spatial statistics, which is called the screening effect. Now, the screening effect is essentially a term that says that if you have a smooth Gaussian process with a slowly decaying kernel, if you condition that Gaussian process, then what you're going to see is that you're going to observe fast decorrelation. So what do I mean? In the setting of a Gaussian process Xi that we have just introduced, what this means is that if you look at the correlation of Xi at the points x and xj, you're going to see that these points are strongly correlated. Why? Because the covariance function, the Green's function, has an algebraic decay. But if instead of looking at the correlation between these 2 points, you look at the conditional correlation, where you condition on the values of xi at all the green points in between them, then what you are going to see is that this conditional correlation has also an exponential decay at a scale that is defined by the typical distance by these green points. And the way you get that result is by observing that this conditional correlation is actually equal to minus the cosine of the angle between these basis functions psi I and psi j. Okay. Now let's look at another problem in multiscale analysis. So this is a problem related to the identification of operator-adapted wavelets. And the question is how to construct wavelets adapted to the operator L. And by adapted, I mean that you want those wavelets to satisfy 3 conditions. So first, you want them to be scale orthogonal with respect to the operator scalar product. Why? Because then if you write your operator L in the basis formed by these wavelets, you obtain a block diagonalization of its matrix representation. Next, you want the operator to be well conditioned within each subband. Why? Because then each one of these blocks is going to be well conditioned. And finally, you want those wavelets to be localized. Why? Because then those blocks are going to be sparse or nearly sparse. And by localized, I mean you want them to be compactly supported or exponentially decaying. Now, there has been several generations of operator-adapted wavelets. The first ones were essentially adapted to the Laplacian or to a homogeneous operator in the underlying space. With the second generation of operator-adapted wavelets, people try to get these 3 conditions to be satisfied at the same time, and the typical process that we used was Gram-Schmidt orthogonalization. But if you do that, one of the 2 other properties, so well conditioning or localization, goes out of the window. And what I want to show you is that, again, if you take this, the perspective of this interplays between stochastic and multiscale analysis, this problem becomes very simple and you can solve it easily. So what do? Well, instead of giving yourself m measurement functions, you are going to give yourself a hierarchy of measurement functions. And by hierarchy, I simply mean that you want these measurement functions to be linearly nested across scales. So here, this k is going to be a label for scale, and I is going to be a label for location in space, and pi is going to be the matrix expressing this linear nesting across scales. So for instance, if your domain is this unit square, you can take those phi k's to be how pre-wavelets constructed as follows. So you take your unit square, you partition it into 4 subsquares, then 16, etc. And you take your level 1 measurement functions to be indicator functions of these 4 subsets, your level 2 measurement functions to be indicator functions of these 16 subsets, etc. And these measurement functions are trivially linearly nested in the sense that this indicator function is a linear combination of these 4, etc., etc. And you can do this for arbitrary domains. It doesn't need to be this unit square. And if you have enough regularity in your operator, so if S is greater than d over 2, then you can take this hierarchy of measurement functions to be subsample masses of Diracs. So what do I mean? Well, for this particular example, you can take your level 1 measurement function to be this Dirac, your level 2 measurement function to be this 9 Diracs, and your level 3 measurement functions to be this 9 times 9 Diracs. And this guy is trivially a linear combination of this one. The underlying matrix pi has an entry 1 for this one and 0 for all these. Okay. Yes? A question? No? Okay. So this is what these basis functions or these pre-wavelets look like. So what I mean here is that once you have these measurement functions, you simply take your underlying Gaussian process C and you condition it on this hierarchy of measurement functions that you have just constructed. And what you obtain is a hierarchy of basis functions that are essentially pre-wavelets adapted to the underlying operator L. And this is what they look like over 7 scales. Now, because these measurement functions are linearly nested, and because, yes?
I think you're okay to continue.
And because this optimal recovery splines are obtained by applying a linear map to this hierarchy of measurement functions, these gamblets are also going to be linearly nested across scales. And the matrix expressing this linear nesting is what you will call the restriction or interpolation matrix in multigrid. Okay. Now, the rest is essentially turning the crank of classical wavelet analysis. So you define Vk as the linear space formed by this psi-Ks. Because these psi-Ks are linearly nested across scales, then you have a Vk minus 1 that is a linear subspace of a Vk. So you can define its orthogonal complement with respect to the energy scalar product. And the question then becomes, what are the basis functions for Wk? Well, you can very simply show that the basis functions for Wk are linear combinations of psi-Ks, and these linear combinations can essentially be obtained by taking local differences of these psi-Ks. The coefficients here are essentially spanning the kernel of these matrices pi's that are expressing the linear nesting between measurement functions. So these coefficients W are essentially the same coefficients that you will take to orthogonalize your Haar pre-wavelets into Haar wavelets. And if you do that with your psi, what you obtain are essentially operator adapted wavelets adapted to the underlying operator L, and you obtain a decomposition, a multi-resolution decomposition of your solution space into a direct sum of subspaces that are mutually orthogonal in energy scalar product. Okay, so these basis functions are localized because there are local differences of localized basis functions that are exponentially decaying. And they are orthogonal, scale orthogonal by construction. The last thing that we need to check is that the operator is well conditioned within each subband defined by these wavelets. And the way to do that is by simply looking at the stiffness matrix defined by these wavelets. This is the energy scalar product of the operator. And if you define Bk to be these stiffness matrices at scale k, you can show that these Bk's are uniformly well conditioned independently from k. And this is an illustration of this phenomenon. So what this plot is essentially showing is the condition number of Bk as a function of k in the blue graphs, and in the yellow graphs, where yellow bars, what you see is the condition number of the AKs, which are the condition number of the pre-wavelets. So these ones blow up, but this one remain uniformly bounded. So essentially, this wavelet decomposition looks like and quacks like an eigensubspace decomposition, but it is not an eigensubspace decomposition, because although you have orthogonality in an energy scalar product, they are not L2 orthogonal. They are essentially nearly L2 orthogonal, but not exactly. So they are not exact eigensubspaces of the underlying operator. So to summarize, what this method has done for you is that it has taken the solution space of your operator L, and it has decomposed it into a direct sum of subspaces that are mutually orthogonal in energy scalar product. And another, from the matrix perspective, it has taken the matrix representation of your operator L and block diagonalized it into blocks that are uniformly well conditioned and sparse. And because you have this sparse block diagonalization, what you obtain at the end of the day is an algorithm that can compute these wavelets in near linear complexity. I'm not going to go over it. And you also get a fast solver for solving this linear system L equals F that operates in near linear complexity. Okay. This is an illustration of this solver. So the way this solver operates is that it solves. So this is an example of application to this divergence form elliptic PDE. And what the solver does is that it solves the projection of U on each of these subspaces that I've defined here independently. And basically what you see here are the projections of U at different scales or at different levels of resolution. The numbers that you see below those subfigures are essentially the energy content of U in each subband. And these numbers go quickly towards zero because here we have a right-hand side that is regular, so you have a numerical homogenization phenomenon. This is another example where the right-hand side is a mass of Dirac. So what you see here is the multi-resolution decomposition of the Green's function of that operator at a particular point. Okay. Now, similarly, you can obtain a sparse rank-revealing representation of the Green's function of your operator. And by sparse, I simply mean that these basis functions are localized, and these matrices are sparse. By rank revealing, I mean that if you truncate it at any scale, you obtain a near optimal low rank approximation of your Green's function. And similarly, you can project the Gaussian process C on these wavelets, and you get a multi-resolution representation of that Gaussian process. I will not go over that. Okay, so now I'm going to move on to a problem in spatial statistics related to the compression and inversion of dense kernel matrices. And this is a joint work with Florian Schäfer and Tim Sullivan. So this is our original operator L that is mapping HS0 into H minus S. We are going to assume that S is greater than d over 2, so that this Green's function G is continuous. We are going to take our domain omega, and we are going to assume that we have n approximately homogeneously distributed points in that domain omega. We're going to call them x1, xi, xn. And by homogeneously distributed, I simply mean that the ratio between any point x in that domain omega and the closest red point divided by the mean distance between any red point and any neighboring red point or the boundary is uniformly bounded by some constant c. Next, we're going to consider the n by n symmetric positive definite matrix theta obtained by looking at pairwise evaluations of that Green's function G at those points xi and xj's. Now, this matrix theta is important in computational physics, Gaussian process statistics, and kernel methods for machine learning. And because it is dense, its manipulation is the main computational bottlenecks in these areas. So naively, if you try to store it, you're going to pay n squared. If you try to do a matrix vector multiplication, you're going to pay n squared. If you try to do an inversion with that matrix theta, you're going to pay n cubed. If you try to compute its determinant, you're going to pay n cubed. And if you try to do a PCA on theta, you're going to pay n cubed. And what I want to show you is that, again, if you take this perspective of this interplay between stochastic analysis and numerical analysis, you can obtain a very simple algorithm for addressing that problem. So the way this algorithm works is as follows. So knowing only the domain omega and the locations of these points xi. So in particular, we do not assume that the underlying operator L is known. So in that sense, there is something there's going to be something universal about that method, in the sense that it applies to all elliptic operators in the same way. So knowing only omega and the location of those points, we are going to reorder those points, which is equivalent to reordering the rows and columns of theta. And we are going to select n polylog n entries of theta, which are going to be the entries of theta that we're going to compute with. So this theta has n square entries, but we are only going to look at n polylog n of them, and we're going to completely ignore all the remaining entries, and we're going to call that the sparsity pattern. And from these entries, we're going to compute a lower triangular matrix L, such that the number of non-zero entries of L is n polylog n. And the claim is that you can do this in complexity n polylog n, where the power in a polylog is 2 times dimension plus 2 in time and space, such that this L forms an approximate Schäfer factorization of theta. And once you have this Schäfer factorization of theta, you can perform all the previous operations in complexity n polylog n, where the power in the polylog is d plus 1. Okay. Now I have this plus 1 and plus 1 and plus 2 in red because in 5 minutes I will show you how to drop them. Okay. Now the underlying algorithm is a simple incomplete Schäfer factorization algorithm. So this is something that you can use off the shelf with a particular sparsity pattern and with a particular ordering. So what you see being illustrated here is the regular Schäfer factorization algorithm. The incomplete Schäfer factorization algorithm is that algorithm with a small trick. And the small trick is that you skip all operations where your algorithms queries pairs of entries that are outside of a given sparsity pattern in your matrix theta. So if this is your matrix theta, you are going to define some entries that you are going to compute with, and you're going to completely ignore all the pairs that are outside of this sparsity pattern. Okay, so how do you define this sparsity pattern? Well, to define it, we are going to take our endpoints. Those are the blue points, so those are the points xi, and we are going to decompose them into a nested hierarchy. So we are going to color some of them in red, and we're going to call them level 1. They're going to be roughly separated by a distance of 1/2. Then we're going to color some of them in green. They're going to be roughly separated by a distance of 1/4. Then we're going to color some of them in brown. They're going to be roughly separated by a distance of 1/8. So they don't need to be on the grid. I'm just using this for illustration purposes. Then from this hierarchical ordering, we are going to define our sparsity pattern as follows. So this is our big matrix theta, and I'm going to show you which entries we are going to compute with. So assume that those are your level 1 points, and this is an I. Then what we are going to do is that we are going to keep all the entries ij's of the matrix theta, such that I is this red point and j is a blue point within that disk of center xi and a radius log of 1/epsilon times 1/2. So log of 1/epsilon is the kind of accuracy that we want to get, approximate Schäfer factorization at the end of the day. So we do that for that point xi, we do it for all our level 1 points, then we move on to level 2 points. But as we move on to level 2 points, we divide the radius of our disk by 2. And again, we do the same thing. If this is xi, we're going to keep all the entries ij of that matrix theta, such that xj is within that green disk. We do the same thing for all level 2 points. And then when we are done, we move on to level 3 points. And again, we divide the radius of the disk by 2 until we have exhausted all our points. And at the end of the day, it is easy to see that what you are left with is a sparsity pattern that has only n polylog n entries as opposed to n square entries. So what you see running here in parallel is the complete Cholesky factorization algorithm, which runs in complexity n cube, and this incomplete Cholesky factorization algorithm that ignores all the entries outside of this sparsity pattern. And this one runs in complexity n polylog n, so it is much faster. And again, this algorithm is oblivious to the exact knowledge of the underlying PDE and uses only the geometry of the discretization. Okay. So why does it work? Well, it works because the hierarchical ordering leads to sparse Cholesky factors. Now, what you have to observe is that the Cholesky factorization algorithm depends on the particular ordering that you are feeding it in terms of the points x1, xn, right? If you change the ordering, you're going to change the Cholesky factors. In particular, if you use the original lexicographic ordering, this is not true that those Cholesky factors are sparse. They are not sparse. So why are those Cholesky factors sparse in the hierarchical ordering? Well, to answer that question, I'm going to call theta k the submatrix of theta obtained by evaluating the Green's function at level k points. And what you have to observe is that a single step of block Cholesky decomposition essentially computes the Schur complement of the block theta k minus 1 of the matrix theta k. And these Schur complements are sparse. Why are they sparse? Well, they are sparse because these Schur complements are equal to the conditional covariance of our original Gaussian process Xi, where we look at the covariance between level k points and we condition on level k minus 1 points. And because of this screening effect, which we already discussed, this conditioning is causing the exponential decay of the entries of that Schur complement. And this SK is therefore sparse. Another way to see that this SK is sparse is by observing that it is the inverse of the stiffness matrix of our opera-adapted wavelets using masses of Diracs as measurement functions. That's also another way to get that sparsity. Okay. So this works with the hierarchical ordering, but this hierarchical ordering is in fact not special. You can also use a random ordering and you're going to get a sparse Cholesky factors. Why? Because a random ordering will implicitly create a hierarchical ordering. So the ordering that we use in practice is simply a max-min ordering of the points. And the idea of this max-min ordering is to simply select one point that is the farthest away from the boundary, then select the second point as the point that is the farthest away from the boundary and the first point, then select the third point as the point that is the farthest away from the first two, so on and so forth. And if we call LK the radius of this of each disk, we can see that this radius is actually going to decay towards zero in a geometric manner. Okay. And the sparsity pattern is simply defined as before. Those are the entries of the matrix theta that we keep or that we compute with. And we define them as the entries ij, such that the distance between the point xi and xj is bounded by some constant rho that is a trade-off between accuracy and complexity. So typically we take it to be of the order of log of n over epsilon. Times the maximum distance between the radius of the disk associated with Li with I and the radius of the disk associated with J. Okay. So in summary, the good thing about this algorithm is that it's a very simple algorithm. It is simply an off-the-shelf iShol algorithm with a particular sparsity pattern and particular ordering. And it only depends on the intrinsic dimension of the data set because you're only querying pairwise distances. So the D appearing in the complexity of that algorithm is not the dimension of the underlying ambient space, but the effective dimension of the data set. Now, the bad thing about this algorithm is that adding a nugget diminishes the sparsity pattern of Cholesky factors. So this is a major open problem in spatial statistics. In practice, what people want to factorize is not theta, but theta plus some scalar times the identity matrix, and this scalar is called the nugget. And another bad thing is that constants can be large, and this impacts both time and memory, so you have to address this if you want to make this algorithm practical. Okay, so in the remaining time, I want to show you how you can do that, and this is joint work with Florian Schäfer and Matthias Katzfuss. And the way we do it is by factorizing the precision matrix instead of the covariance matrix. And the reason why this works is because the Cholesky factors of the precision matrix in reverse ordering are sparser than those of theta. And the reason for that can be seen by considering the Gaussian vector with mean 0 and with covariance matrix theta, and observing that although theta is dense, its inverse, the precision matrix, is sparse. And the reason why it's sparse is because it is proportional, its entry ij is proportional to the conditional covariance between x and xj. And again, the screening effect is causing a sparsity for us. Another reason for factorizing the precision matrix instead of the covariance matrix is because the Cholesky factors of the precision matrix plus a nugget remains sparse despite the addition of the nugget. And because they remain sparse, this solves this open problem in special statistics. What do I mean? Well, if you want to factorize this, then you can write this expression as theta times this expression. And then you can factorize theta and theta minus 1 plus the nugget independently, and then you get a factorization algorithm that is robust to the introduction of nuggets. Okay. But the problem is, how do you do that? How do you directly compute the Cholesky factors of the precision matrix when you only have access to the entries of the covariance matrix? And again, here the solution is given to us by looking into stochastic analysis and to the underlying Gaussian process interpretation of that matrix theta. So what do I mean? We are going to recover those Cholesky factors by solving an optimization problem. And the optimization problem is as follows. We're going to look for a lower triangular matrix L that minimizes the Kullback-Leibler divergence between a Gaussian distribution with mean 0 and covariance matrix theta, and a Gaussian distribution with mean 0 and covariance matrix, the inverse of L transpose, while L is a lower triangular matrix with a given sparsity pattern, which we have already defined. Okay. So in that sense, instead of letting the incomplete Cholesky factorization algorithm find that matrix for us, given the sparsity pattern, we're going to try to solve this optimization problem and get it directly. Well, the surprising thing here is that this optimization problem can be solved explicitly, and this is the formula for it. I'm not going to go over it. The main thing is that to find it, you only need to query the entries of theta in the sparsity pattern. And this expression allows you to compute all the columns of that lower triangular matrix L in parallel. Now, the expression itself is not new. It is known as the Vecchia approximation in special statistics. What we have done here is to simply observe is optimality in Kullback-Leibler divergence and use it to obtain this Cholesky factorization of the precision matrix. So at the end of the day, if you take this approach, you get the following algorithm that computes the Cholesky factorization of the precision matrix in complexity n polylog n. And the difference between the previous one is that you have 1 or 2 log factors less here. And in fact, the other difference is that this L has some optimality to it. And because it has some optimality to it, this algorithm has some important features that make it practical. So first, it has small constants. You can use it to invert a 1 million by 1 million matrix in 10 seconds on a single core. So you can do it on your laptop. L is optimal in Kullback-Leibel divergence, so the approximation is always positive definite. The columns of L can be computed in parallel, so if you give yourself 1,000 cores, you can Schwarzschild factorize 1 billion by 1 billion matrix also in 10 seconds. Often there is no need to form L, you just want to do matrix vector multiplication by L in Gaussian process regression, for instance. So in fact, the memory footprint of this algorithm in this situation is linear in M. It can be extended to sums of independent processes, so to the factorization of theta 1 plus theta 2, where theta 1 and theta 2 are of the form that I just described. So this solves a major problem in computational statistics, and you only need pairwise distances of the xi's to make it work. So this algorithm is oblivious to the ambient dimension. It depends only on the effective dimension of the data set, and it doesn't need to know what the underlying operator L is or the underlying Green's function G is. So in that sense, there is some kind of universality with respect to the homogenization of all elliptic operators mapping HS into H minus S. Okay, so I'm running out of time, so I will skip this and I will end the talk here.